Ampere's law. The electric field was first calculated by choosing a small piece of charge on a symmetric shape, there's that word again, finding the field due to that charge and then adding them up using integration techniques. Gauss's law simplified this process, but again only for very symmetric shapes. Now let's go to magnetic fields. First, we use the Biot-Savart law to calculate the magnetic field due to an extended current distribution. Now second, do you think there's an analogous process that can be used to simplify that? I hope so. In other words, just like Gauss's law simplified the process of finding the electric field. Probably can guess, I mean it's in the title here. Ampere's law. Magnetic field lines circle a current carrying conductor. Here's our conductor here, carrying current out of the page. You find the direction of the field lines using the right-hand grip rule. Place your thumb in the direction of the conventional current coming out of the page and curl your fingers around the conductor. That's the right-hand grip rule. So it tells you that your magnetic field lines circle like this, and of course the magnetic field at any point will be tangent to that circle. The strength of the magnetic field is the same at all points because it's the same distance from the wire. B, the magnetic field, is always going to be parallel to a line segment, ds, that is tangent to the circle. So here's ds and here's B. You go anywhere on that circle, you can draw the same thing. So B dot ds will always be B ds, the magnitude of B times ds. The next step is to sum up the dot product of B and ds around the entire closed path defined by the circle of radius r. And remember how we said that B dot ds is just going to be B ds. And then substitute in for B the value of the magnetic field that we found from Biot-Savart. So what we're left with is over here, okay, we have the value of B, and we add up all the little ds's. We do a line integral there, add them all together, and what do we get? Well, we get the circumference of the closed path, which is 2 pi r. Things divide out, and we have the closed path integral, the line integral of B dot ds over this line here, the circle, the circumference, is equal to mu 0 I. This is Ampere's law. The dot product enables you to choose any symmetric shape, there's that symmetry word again, about a current distribution, and the law still holds. I will be the current passing through a surface that is enclosed by the chosen Amperian loop. Very similar to the Gaussian surface when we use the surface integral. So another big difference here, Gauss's law had a surface integral, Ampere has a line integral. This guy looks the same, so you have to know, which law you're applying it to. And it helps that this is just a line segment, so you know that that's a line integral. We indicate an Amperian loop with a dashed line, just like we did for the Gaussian surface. So there's our Amperian loop. There are limitations. Ampere's law only works for constant currents. In addition, no magnetic materials can be nearby, and there can be no time-varying electric fields. Ampere's law was modified by James Clerk Maxwell by adding the displacement current. That's a current that really doesn't exist between two sides of a capacitor, and hopefully we'll get to that a little later. But here's the Ampere's law I just showed you. Maxwell completed it by adding a time-varying electric field. This was actually the only physical property that Maxwell added to Gauss's law for electricity and magnetism, Faraday's law of induction, and Ampere's law to come up with the mathematical formalism that describes electricity and magnetism, which is known as Maxwell's equations, and we'll be coming to that in the next unit. These four equations, unlike Newton's laws, right, F equals ma, inertia, stuff like that, they did not have to be modified by Einstein's theory of relativity, of special relativity. They already fit in.